Good morning, friends. This is my next lecture on the same topic, that is the chemical thermodynamics. And today we are going to discuss the new point from that is the enthalpy of solutions. In last video we covered the enthalpies related with the physical transformations, and in that we covered enthalpy of phase transition, that is enthalpy of fusion, enthalpy of freezing, enthalpy of vaporization, enthalpy of condensation, enthalpy of sublimations, and enthalpies of atomization, enthalpy of ionization, electron gain enthalpy, and all these things, isn't it? So as far as enthalpy of solution is concerned, so enthalpy of solution is nothing but the enthalpy change occurs. Enthalpy change occurs when one mole of solute when 1 mole of solute is dissolved in specific amount of solvent. When 1 mole of solute is dissolved in specific amount of solvent so as to form a solution of specific concentration, isn't it, or definite concentrations. So whenever one amount of solute is dissolved in specific amount of solvent so as to form a solution of particular concentration, this is called an enthalpy of solution. This is called enthalpy of solutions. And remember well, mind well, that is the enthalpy of solution is not directly determined. Okay, means when solute is added in solution and enthalpy of solution is obtained. It is not the case like that one. Before that, when dissolution process or formation of solution is concerned, if formation of solution is concerned from any solute is dissolved in solvent, when formation of solution is concerned, one, then it involves three steps. Generally it involves three steps. One, that is first step, that is the solute particles which are present, there is a separation must occurs. Okay, separation between solute particles must necessary one. Second one, that is the separation between solvent molecules, also very important one. Separation between solvent molecules is very important one to accommodate that dissolved solute particles. And last one, that is the solvation process. And if water is there, it is hydration process. And then finally we say that the added solute is get completely dissolved. Means a dissolution process is not a single step or one step process. Means when you add sugar or salt in water one, then it directly dissolves. We say that is NaCl or sugar dissolves completely in solution. But actually behind the process or mechanism of the dissolution one, three steps are involved. First, there must be separation of ions, isn't it, from that solute one. Second one, to accommodate that solute particles in solution, solvent molecule has to go away from each other. And lastly, that is the hydration process. If water is there one, or solvation process takes place one, and then we say that the solution is formed from that particular solute one. Now, here if enthalpy of solution is concerned, enthalpy of solution is not a single directly obtained one. Okay, so during all these courses, whatever enthalpy change occurs in all these course, during the separation of solute particles, during the separation of solvent molecules, and in the hydration process or solvation process, all these enthalpy changes, if we add all these enthalpy changes or energy changes in these things one, then we get the total enthalpy of solution. So enthalpy of solution is nothing but the sum of the enthalpy change occurs in all the individual steps, one, while from adding the solute into solvent till the solvation process is there one. And then there is the first important thing for determination of enthalpy of solution, that the solute particles as far as concerned one, that solute particles, if you consider solute particles, these solid particles must be what we call as intermolecular force or interionic forces which is present one. Intermolecular or interionic force of attraction which is present has to be broken. Then and then only it is the first prerequisite, what we call as a step in the formation of solution. It is the first important step in the formation of solution. If the solute is, suppose mx is the solute one, then when mx is added in water, and any other desired suppose solvent one, then first important step, that the bond between m and x, this bond has to be broken. And this m and x must be separated from each other one. And during this course, during this course, whatever enthalpy change occurs, that enthalpy change, if substance is ionic in nature, if substance is crystalline ionic in nature, then in that case the enthalpy change during the breaking of that interatomic or interionic bond from that ionic solids one, when substance is ionic one, in that case the enthalpy change occurs. It is called as that is a lattice enthalpy. It is called lattice enthalpy. Simply it is called lattice enthalpy. Remember that. It is called lattice enthalpy. It is called lattice enthalpy. Okay, when ionic compound is there. When ionic compound is there. Represented by symbol that is a delta LH. Represented by symbol delta LH. Delta H enthalpy change. And here word L is used capital because that represents lattice. That represents lattice one. Now lattice enthalpy as far as concerned. Lattice enthalpy as far as concerned. Lattice enthalpy we consider two types. Actually lattice enthalpy are of two types one. That is the and lattice enthalpy of, that is the dissociation enthalpy, lattice enthalpy of dissociation, lattice enthalpy of dissociation, and second one lattice enthalpy of formation. Lattice enthalpy of formation. So lattice enthalpy of dissociation and lattice enthalpy of formation are the two types. Okay. Now as far as lattice enthalpy of dissociation is concerned, lattice enthalpy of dissociation is concerned, one means when 1 mole of crystalline solid substance, ionic solid, when 1 mole of crystalline solid substance, okay, 1 mole of crystalline solid substance is converted into, means by breaking the interatomic bond one, is converted into its corresponding gaseous scattered ions, in corresponding gaseous scattered ions one, then during that course whatever enthalpy change occurs, that enthalpy change is called as lattice dissociation enthalpy, delta LH, but it is dissociation. It is dissociation. This crystal, not necessary to write dissociation here. Actually, it is, now see, the bond between M and X, this bond has to be broken. So external energy is to be given. So in this case, delta LH is positive. Delta LH is always positive for the dissociation process. For dissociation process one. So lattice enthalpy two type. Dissociation, the bond between M and X has to be broken, M plus and X minus in the gaseous scattered form मध्ये separate करण्यासाठी लागणारी enthalpy, it is called lattice dissociation enthalpy or lattice dissociation enthalpy one, isn't it? Second case, that is formation enthalpy, that is the from scattered gaseous ions, if it results in the formation of 1 mole of MX solid, 1 mole of crystalline solid is formation. During that process here bond between M plus and X minus gaseous, this formation takes place, bond formation is involved. That's why it's called crystal, that is the dissociation, lattice enthalpy of formation, and here the lattice enthalpy of formation delta LH, here bond formation are always exothermic, heat energy is given, that's why it is negative. So remember well, actually that is the just lattice enthalpy is the concerned, enthalpy of dissociation, enthalpy of lattice, or lattice dissociation enthalpy, and that is formation enthalpy. Same process is there. When substance bond breaking process occurs, it is dissociation. Bond formation, it is formation enthalpy. That is enthalpy of formation. And out of these two cases, if you considered in the formation of solution, we are not going to form a crystals from its gaseous scattered ions. We are going to consider this reaction. That is the substance from the crystal substance, that is the crystal ionic substance, scattered gaseous ions are separated. So we are interested in the dissociation, that is lattice dissociation enthalpy, and lattice dissociation enthalpy is always positive. And for sodium chloride from Born-Haber cycle, which you all may studied in the 11th standard one, from Born-Haber cycle, this crystal lattice enthalpy for NaCl is determined. It is about 790 kilojoule per mole. It is 790 kilojoule per mole plus 790 kilojoule per mole for NaCl, sodium chloride is determined. Okay, so this is lattice dissociation enthalpy. More the value of lattice dissociation enthalpy, stronger the bond between M and X. Stronger the bond between M and X means if lattice enthalpy ची व्हॅल्यू जितकी वाढेल, लॅटिस डिसोसिएशन एंथॅल्पीची जितकी व्हॅल्यू वाढेल, त्याचा अर्थ असा झाला की एम अँड एक्स मधला बॉन्ड जो आहे तितका स्ट्रॉंग असणार. बॉन्ड काय असणार आहे? स्ट्रॉंग असणार. आणि लॅटिस डिसोसिएशन एंथॅल्पी व्हॅल्यू जितकी कमी असेल तितका बॉन्ड बिटवीन एम अँड एक्स इज वीक. सो लेस एनर्जी इज रिक्वायर्ड टू ब्रेक दॅट particular bond and to separate into gaseous ions, isn't it? So it is the first step involved in the formation of solution, that the added solute madla interatomic bond किंवा interionic bond has to be broken and it is converted into corresponding ions one, And when substance is ionic one, then we consider the enthalpy change is nothing but it is called lattice dissociation enthalpy, simply called as crystal lattice enthalpy, represented by symbol delta LH, and it is always positive. It is always positive. For Bohr-Neighbor cycle, for NaCl it is determined, it is plus 790 kilojoule per mole, isn't it? So this is the first step. This is the first step involved in the formation of solution one, isn't it? Now, first step is over, completed, means ions are formed in the gaseous state one. But ions which are formed in gaseous phase one, okay, ions which are formed from mx, ions are formed, that is m plus x minus, x minus. But these ions are present in solution itself. These ions are present in solvent, okay, solvent. These ions are present in solvent, okay, solvent मध्ये असणारे ते ions just I shown by red color, it is as m plus, here suppose m plus, and here suppose x minus, and here in black spheres I will going to show these are the what we call as a solvent molecules. Initially solvent molecules, as far as concerned, initially solvent molecules, there is a what we call as a intermolecular force of interaction between two solvent molecules. Between two solvent molecules there is intermolecular force of interactions, and due to that intermolecular force of interactions, all solvent molecules, okay, in all solvent molecules there is a what we call as intermolecular force of interactions. Due to that, when mx is converted to m plus and x minus 1, then m plus and x minus has to be what we call as accommodated in that solvent, and for that accommodation solvent molecules has to go away from each other. Means in short we say that there is a breaking of molecular forces, that is the weak van der Waals forces which are present in between two molecules has to be broken, and then only these solvent molecules goes away from each other. It will goes here, and one room or space is created one where the m plus and x minus is accommodated. Means in short we say that there is a second step, that is for the accommodation of the dissociated ions. In the solvent molecule has to go away from each other. They has to prepare the room or space for the ions. And remember well, solvent molecules as concerned, these solvent molecules, if there is molecular force of interactions, one weak van der Waals force of interaction is there, then this bond has to be broken. In the sense, this process is endothermic. External energy is necessary here one. Okay, external energy is necessary. So it is endothermic process one. Okay, second step. Then next, third step one. If they goes away from each other, then next step, yes, the water molecules which are present here. Suppose water is the solvent used here. Water molecules which are present one, or any polar solvent if present one. Water or any polar solvent. These polar solvents surrounds the positively charged cation, and this polar solvent surrounds the negatively charged anions from the opposite end of solvent. If water is the solvent, it is minus delta plus delta plus delta. So this water surrounds the m plus from its oxygen end, because negative it is positive, and this water surrounds the x minus ions by means of its hydrogen ends or terminals one. And due to this solvation process, it stabilizes that ions one, because individual ions are unstable one. Individual ions are always unstable one, and due to that it provides stability one, and during that stability energy whatever released one, that is used for the what we call to move the solvent away from each other, one, isn't it? Same energy is reversed. This process is called as an solvation. In which the particular ions may be cations or anions of solid particles, when surrounded by solvent molecules to get stabilization, the process is called as an solvation. But if water is there one, that process is called as an hydration. Process is called as an hydration process. That process is called as an hydration. Remember well, isn't it? So again, the data means external data study says that the hydration enthalpy for, just if you consider like this one, if you consider hydration enthalpy, then suppose m plus is there, okay, m plus is there gaseous. It is suppose x moles of H2O, it is converted into, that is the M H2O X plus. Okay, MH2O X plus, and suppose X minus is there gaseous plus Y moles of H2O, it converts into X into bracket H2O Y moles minus 1. So this is hydration. And during the course, the enthalpy, this is called as a delta hydration enthalpy. And this delta hydration enthalpy is always negative. It is always negative. It is always negative one. So that's why. So two enthalpies we covered up to now. That is the first one. That is the hydration enthalpy is negative always. So overall enthalpy of solution, if you want to calculate, it is a delta solution H is nothing but crystal lattice enthalpy plus hydration enthalpy, means delta LH plus delta hydration H. And for sodium chloride, for NaCl, delta hydration enthalpy is found to be minus 786 kilojoule per mole. Minus 786 kilojoule per mole. So through the values, crystal lattice enthalpy for NaCl determined from Bohr-Haber cycle, it is 790 plus 790 plus minus 786. It becomes plus minus minus, isn't it? So it is plus 4 kilojoule per mole enthalpy of crystal lattice, enthalpy of solution. Means when 1 mole of NaCl is dissolved in water, then how much amount of energy is released? How much amount of energy is required for the dissolution process? 4 kilojoule. 4 kilojoule is required energy. This much amount of energy required for the dissolution of 1 mole of NaCl in water. 1 mole of NaCl in water. So this is overall about enthalpy of solutions. Hope you understand all these things. Enthalpy of solutions. Okay. Good day.